Hello. So today I want to discuss about a problem that appeared in CMI entrance exam 2013. It's a problem on functions, mainly involving injectivity and surjectivity. Seeing this video will give you a general idea to how to solve this type of questions, and it's a really common problem. At the end of this video, I'll give you a similar type of problem to try out on your own. After you have found out the solution, you can type your solution in the comment box.
This video is sponsored by Chinta.com. Since 2010, Chinta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
So now let's begin. So I have two sets A and B, and f from A to B and g from B to A are two functions such that f of g is the identity function. Like f of g of x equal to x for all x. I have to check the statements whether for that f must be 1, 1 or onto or not, whether g is 1, 1 or onto or not, like which of the statements must hold. So let's begin. Remember, for any two functions f and g, if f of g is bijective, that would imply g is 1, 1 and f is onto. This must hold. Why? Let's say, so f from A to B and I have g from B to A. So f of g is, its domain is, g's domain is B, it's from B to B. Say r of x equal to f of g of x, and r is bijective, I know that. So now I have to prove that g is 1, 1 and f is onto. Now g of x1 equal to g of x2, that would imply you will apply f on both sides, so f of g of x1 equal to f of g of x2. So r of x1 equal to r of x2. Now as r is bijective, so r is 1, 1. So r is 1, 1. So r of x1 equal to r of x2 implies x1 equal to x2. So I started with g of x1 equal to g of x2 and I got x1 equal to x2. So that would imply g is 1, 1. Similarly, to get f is onto, we know that r is onto. So for all b in B, there exists, say, k suffix b in B such that r of k suffix b equal to b. Now we already know that r of k suffix b is just f of g of k suffix b. So I get that f of g of k suffix b equal to b. So for any element of b, preimage of b under f is just g of k. That means f is onto, because any element has a preimage. So these two conditions must hold. Thus in our questions, here f of g is identity on the set B. So in this case, as it is an identity, is always bijective. As f of g is bijective, the g must be 1, 1 and f must be onto. Now these are the conditions we need. Now we need to check that whether the other conditions we need or not. I claim that we don't need that. For example, you can construct a lot of functions. There are many examples possible. I'll give a particular example. Say f is from R2 to R, g is from R to R2. That f maps x comma y to x. So f is just a projection, like if it maps any point in R2 to its just first x coordinate, like it's just projecting one coordinate, and g of x equal to, you can put it whatever, you can say it x comma 0, or you can define it to be x comma x also, doesn't matter. There are many ways possible. So these are my definitions of f and g. Now f of g maps from R to R. F of g of x equal to f of x comma 0 or f of x comma x, whatever. It depends on how I define. In either cases, it is just x. So from here I get that f of g is just identity of R, identity function on R. So as I got, f of g is identity, but you can see, we know that g is 1 1 and f is onto from definition. Like g of x is just x comma 0. So x1 comma 0 equal to x2 comma 0 to imply x1 equal to x2 by definition of equality of coordinates. So g is 1 1 and f is onto over R, because for any element x my pre-image would be x comma anything, like, but it is not 1 1, you can see that. You can see g is from R to R2, but g is not onto and f is not 1 1. Because what does my f do? F maps any point to its just first coordinate. Now, like this is my x, this is my y, this is my point x comma y. So f maps this to just, f just drops by coordinate, like it projects it onto this x-axis. This is the action of f. We can easily see that, like, for any, like if I fix x and vary over y, all points give me the same x, like any element has infinitely many pre-images, so f is not 1 1, f is onto but not 1 1, and similarly g is 1 1 but g is not onto, because what does g do? G just maps x comma 0 to just x, g maps my x to x comma 0, R to R2. Now if I vary over x, so x comma 0 just is the only my positive real axis, sorry, just real axis, not positive, and it doesn't cover any coordinate that has any non-zero y coordinate, so it does not cover any other part of R2, so g is not onto. So g is not onto, f is not 1 1, but we have f of g is identity. So f of g is identity, but f need not to be 1 1 and g need not to be onto. So that's it, and we are done. So as promised, I'll give you a similar type of problem. So the problem is, A is a subset of R. A is bounded. F is a function from A to A such that mod of Fa minus Fb, that is same as mod of A minus B for all A comma B in A. You need to prove that F is bijective. See that the 1 1 part is very easy. Like if you take f of a1 equal to f of a equal to f of b, then you will get that mod a minus b equal to 0, so a equal to b. That's true. So the main interesting part is the onto part. You try that on your own, and if you found out the solution, you can type that in the comment box. And keep that in mind that you cannot use anything of like continuity and differentiability, because a is an arbitrary subset of R. A can be a subset of natural numbers also. Like if A is a subset of natural numbers, like if A is a discrete set, in that case, like there is no notion of continuity and differentiability stuff. Like those doesn't make any sense. So don't try to involve anything of that. Just do it purely set theoretically and use the fact that A is bounded. Try that on your own. And if you find this type of videos interesting, so you should follow this channel because there are a lot of interesting videos here. Thank you.
Chinta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Chinta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Chinta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit chinta.com.